How's it going, everybody? Welcome to some exam review. We've got a whole bunch of data for you today, and we're going to walk through several different kinds of statistical analyses that you're definitely going to want to know for the exam. So let's take a look at the data. I've got, looks like 20 participants. We've got a variable on their relationship status, whether they're single or currently in a relationship, whether they play Pokemon Go or not, yes or no. The hours they spend outside, let's say that's a weekly number of hours outside. Expenses for Halloween and expenses for Valentine's Day. Okay. What I've got over here on the right-hand side are all of the different kinds of equations that we're going to need to answer some questions about the data. So you can see up here, this is going to be our equation for a one sample z-test, where you have the sample mean minus the population mean over the standard error, which is standard deviation of the population over the square root of the sample size. If you don't know the population standard deviation, which you would only know it if I gave it to you in the prompt. We don't often know that value. If you don't know this, you got to use this, right? This is a one sample t-test, and you estimate the population standard deviation based on your sample's standard deviation, right? And then this bottom term is no longer the standard error, it's the estimated standard error, right? But otherwise, these two equations are almost identical. Moving down to the paired samples t-test. This is how you do it. Paired samples t-test is quite nice because you actually don't have to know that many pieces of information. You're going to need to know the mean of the difference scores and the standard deviation of those different scores, and then the square root of the sample size. And that's pretty much all you need to know. So those ones are pretty nice. Now, independent samples t-test, those are going to be a little bit more work, right? Ultimately, we're trying to end up with this equation here, in which we're subtracting the sample means from each other, or the group means from each other, and we're dividing that by also the estimated standard error, although it's going to be a lot more to calculate the estimated standard error in this case. We don't really worry about this top right portion at all because it's going to say that this is the null hypothesis. This is represented, I think, at least the null hypothesis would say, that there is no significant difference between the population means, the true population means. Well, if that's the case, if there's no difference between these means, they're the same number. And if you subtract the same number from itself, you get zero. So you don't even have to worry about this whole top right portion, similar to how you don't have to worry about it in the dependent samples t-test or paired samples t-test. But in order to get estimated standard error in an independent samples t-test, that's quite a bit of doing, because you can see right here, we need to first find pooled variance of the two samples, divide those by their respective sample sizes, add them together, and take the square root. But we don't know how to get pooled variance, so we need another equation down here, right? This is pooled variance. The sums of squares for group 1 plus the sums of squares for group 2 divided by, you could think of this as the total degrees of freedom, or the degrees of freedom for group 1 plus the degrees of freedom for group 2. Each of those has a degrees of freedom of n minus 1, or you could think about this whole denominator together as the entire number of people in the sample, so n minus 2. All of the people in the entire study, I should say, not just in each of the samples. All of the people in both of the samples combined, and subtracting 2 from that, so n minus 2. Degrees of freedom are going to be n minus 1 for one sample t-test. Degrees of freedom are n minus 1 for a paired samples t-test, and degrees of freedom are going to be n minus 2 for an independent samples t-test. So I would definitely write all these equations down, keep them very handy for you when you're going through the exam. I would also memorize or write down the degrees of freedom for each of the t-tests. All right. So when we look at all this data and all these different kinds of variables, we also want to ask ourselves, well, what kinds of tests could I create from this data? Like, this would be a good opportunity for you to pause the video. Think about how these data are set up, what the variables look like, and what are like, how would you make a one sample z-test from a particular variable? How would you make a one sample t-test from a particular variable? How would you think about running a dependent or a paired samples t-test? Which variables would you look at? For an independent samples t-test, what would you look at? So let's just kind of go through a couple of examples of that, right? If I think that, let's say, people on average spend more money on Halloween compared to spending money on Valentine's Day, what kind of test is that? Well, we're testing two different variables or two different measurements on all of the same participants. So that would be a dependent samples t-test or a paired samples t-test, right? If I said, I think that people who are in relationships spend more money on Halloween than people who are single. What's that? Well, then we've got two different groups, single people and people who are in a relationship. And I want to know if they spend, on average, different amounts of money on Halloween. Well, that's an independent samples t-test, right? Independent samples t-test, because there's two separate groups of people. Similarly, for Pokemon Go, I could say, I think people who do play Pokemon Go spend more hours outside than people who don't play Pokemon Go, right? What's that? Well, it's the same thing. There's two different groups of people, and we're trying to compare them in terms of some variable. In this case, the hours they spend outside each week. So that's an independent samples t-test. How about a one sample z-test? Well, I could ask you something like, I think that people in our sample spend less time outside compared to the average population, or the population average, I should say. If I gave you the population standard deviation as well as the population mean, then you use a one sample z-test. If I only give you the population mean and no population standard deviation, then you have to use a one sample t-test to look into that. Okay. So it's always a good idea to just be thinking about, well, what are the different tests you could potentially run from these data? But I've got some specific questions for us. So we're going to look at this first question here. I think participants in our study spend more money on Valentine's Day compared to the general population. Okay. The mean amount the population spends on Valentine's Day is $100. What is the value of the statistic you found using the appropriate test? Well, first of all, you need to know what the appropriate test is. So you have the population mean. What do you think the right test is going to be to run here? It's going to be a one sample t-test, right? Because you're given the population mean, but no population standard deviation to go on. All right, so I think that participants in our sample are going to spend more money on Valentine's Day than the population average, which is 100. So let's go take a look at that. This is where we want to end up, right? We want our sample mean minus the population mean divided by sample standard deviation over the square root of sample size. So if we were going to do that, well, we've got the population mean, which is mu, right? And mu is $100. We know that mu is $100 for this test, okay? For this population, rather. But we are interested in understanding whether our particular sample is going to spend more money on Valentine's Day than that. So what you have to do is, first of all, figure out, well, what is the average amount that our population spends on Valentine's Day, right? So you're going to calculate the mean. The mean here, you type in equals average is the function to find the mean, and you just highlight all of the numbers that you want to find the average of, hit enter. We've got an average of $60.85. Okay, so now we are going to see, is $60.85 significantly different from an average of 100 or not? We already know that my hypothesis is kind of shot, right? Because I thought that our participants would spend more money on Valentine's Day than the general population. But you don't just stop. You could actually figure out if those two numbers are still significantly different, just maybe in the opposite way that you predicted. So let's find out if that's the case. So what do I need to do? Well, first of all, we have the sample mean, we've got the population mean. We also need to find the sample standard deviation. So let's do that. Standard deviation here. And the function for that is stdev.s, stdev.s. I'm going to figure out that. Okay, here's the standard deviation of amounts of dollars spent on Valentine's Day in our sample. So now, if you want to figure out what t is, well, first of all, I guess we should probably figure out what the square root of n is, because we're going to need that to calculate the estimated standard error. Well, there's 20 people here, and so the function here, and you could just do this on a calculator if you want, SQRT of 20. All right, so that's the square root of 20, 4.47. And now, if maybe I'm gonna drag this over here, then we could just put in 100 down here. So now I've got all the numbers that I need, basically, to solve for t. If I ask you to solve specifically for the estimated standard error, then you're going to take the standard deviation and divide it by the square root of n, right? Standard deviation divided by the square root of n. You need to do that. But if if we don't have to do that step, but you probably will, so remember how to do that. If we just want to go straight for the t-score, or t-value, what I'm going to do is type in equals, and then I'm going to do some parentheses that'll help us with order of operations. So it's our sample mean minus the population mean. I'm going to close those parentheses off and divide by the standard deviation over the square root, not that one, the square root of n, right? So that's what this is saying. The sample mean minus the population mean divided by standard deviation over the square root of n. Let's see what we end up with. Negative 4.31. Okay, well, we still don't know if this difference is significant between our sample mean and our population mean until we compare this to some kind of critical value on the t-table. So in order to think about how we're going to find the critical value, the three pieces of information you need to know are, is it a one-tailed test or a two-tailed test? What is alpha? And what are the degrees of freedom, right? Well, we're using a one-tailed hypothesis, right? Because we're saying, I think participants spend more money on Valentine's Day than the general, population. Obviously, we're going to be wrong, but we can still look up in a one-tailed test whether or not these two means are significantly different from each other. And we needed to know that alpha is 0.05 and degrees of freedom are, for a one sample t-test, are n minus 1. Okay, there's 20 people in this sample. So let's go to our t-table. 20 minus 1 gives us the degrees of freedom of 19. It's a one sample, or I'm sorry, a one-tailed test of alpha is 0.05. So our critical value here is 1.729, or really negative 1.729, negative 1.729. That's the t-crit. Because we're going to compare it to this negative number. So we are definitely wrong in terms of our hypothesis that we thought that our sample's going to spend significantly more amounts of money on Valentine's Day. But in this case, it is still true that because negative 4.31 is significantly different from negative 1.73, that there is still a statistically significant difference between the sample mean and the population mean. It's just not in the direction that we had originally hypothesized. Okay, so on an exam, you could still say that you're going to reject the null hypothesis because in a one sample t-test, the null hypothesis is that the sample mean is not statistically significantly different from the population mean. So you can still reject the null. It's just that your alternative hypothesis is kind of still wrong in that case. So you just have to kind of mention that if you were writing this up in a paper or something like that. Okay, so that is one sample t-test. Let's keep going. Let's see what else we've got brewing here. Question two. I think that participants spend less money on Halloween compared to the general population. The general population spends $80 on Halloween on average, with a standard deviation of $40. What is the value of the statistic you'd calculate for this? Well, first of all, which test are you going to run? Well, you're given the population mean and the population standard deviation. So this is going to be a z-test, right? So we're going to use this equation right here for the z-test. And we're going to, again, look at the difference between sample means and population means. Well, this is for expenses for Halloween. So I'm going to first calculate the sample mean, right? Sample mean for this equals average. Sample mean. Our sample mean is 57.15. And we know that mu, we said was $80. Okay. And we also know that the sigma, which is the population standard deviation, was, if I remember correctly, was $40, right? Yeah, $40. Okay, so $40 there. And we're basically there. I mean, we have like all the pieces of information we need. We've got the square root of the sample size, which we've already calculated right here. So you can just use that same number, or if you want, you can recalculate it just for kicks. Equals SQRT of the number 20 participants. Okay, so instead of a T, it's going to be a z-score, a z-score. And according to this formula, we need to take sample mean minus population mean divided by the standard error, which is sigma over the square root of n. So let's do that. So equals, I'm going to put some parentheses here again to help us with order of operation. Our sample mean minus our population mean divided by, and again, if I ask you to calculate standard error, what are you going to do? You're going to take sigma, which is the population standard deviation, and divide it by the square root of n. That's what you would do, right? I'm kind of skipping that step so we can get right into the test statistic. In this case, it's a z. But on the exam, I'll probably ask you, hey, you're going to probably want to calculate the standard error or estimated standard error in the case of t-tests. And you just got to remember what you're trying to do there. Okay. Let me know if you have any questions about that. All right, so that's divided by, again, sigma over the square root of n. Sigma divided by the square root of n. And let's see what we get. Okay, nicely done. So negative 2.55. So in this case, well, we do know that our sample mean is lower than our population mean, but the question is it significantly lower, right? And so we've got this t-crit of negative 2.55. And again, we're going to be looking up, well, what kind of hypothesis did we have? We had a one-tailed hypothesis because it was directional. Degrees of freedom for a z-test. Oh, wait, you don't need degrees of freedom, right? Because we're going to use not the t-table, but the z-table, right? Now, again, you can memorize the critical cutoff values for a one-tailed test or a two-tailed test if you want to, or you can look it up on the chart. So let's go ahead and look it up on the table, right? We're using a one-tailed hypothesis. So I'm going to look up on the normal table, the normal distribution table, which is also called the z-table. I want to know where in the smaller portion is equivalent to 0.05, right? 5% of the distribution, because that's our alpha. And so I'd go down and I'd try to find 0.05. Now, there's not an exact 0.05. There's either a 0.0495 or a 0.0505. And so you'd want to be right in the middle of that. But anyways, if you follow that over, you find a critical z-score of either 1.64 or 1.65. Most statisticians use the value of 1.64 for whatever reason, but you get the similar answer regardless. So 1.64. Now, it's actually negative, excuse me, negative 1.64 because we're looking at the left side of the distribution because we're interested in whether our sample mean is lower than our population mean. Well, is negative 2.55 more extreme than negative 1.64? Yeah, it definitely is. So it's going to fall into the critical region, and therefore we would reject the null hypothesis. The null hypothesis in a z-test is that, again, the sample mean is not statistically significantly different from the population mean. Well, we've just found that we can reject that null hypothesis and conclude that, in fact, our sample mean is statistically significantly lower than the population mean. All right, that's a couple of tests down. Let's try one with a dependent samples t-test. Oh, I gave it away. All right, question 3. I think people spend more money on Valentine's Day compared to Halloween. What is the value of the statistic you would calculate here? Well, which test are you going to use? I think people spend more money on Valentine's Day compared to Halloween. Okay. Well, we're comparing expenses on this variable to expenses on this variable, or I should say the average on this variable and the average on this variable. Every single participant was measured on both of those variables. And so if we're comparing across two different variables or even two different time points or something like that, within the same group of people, that is a dependent samples t-test or a related samples t-test or a paired samples t-test. All those things mean the same thing, right? Okay. So we've already calculated the means for these things, which is cool. But what we need to do is actually find the difference scores and take the mean of that. So we're not actually that interested in all of the stuff that we've already calculated. We're going to have to create a new column of data that is the difference scores, okay? And you could make it, anything that helps you remember what this is for specifically, because you might have tons and tons of variables, and you want to know that this is the difference between Valentine's Day and Halloween, for instance, or something like that. So we could call it like the difference holiday or whatever you want to call it. So what we're going to do here, we're going to think about in which direction we're interested in. I think people spend more money on Valentine's Day compared to Halloween. More money on Valentine's Day compared to Halloween. Okay. Well, then we're probably going to want to take the Valentine's Day scores and subtract Halloween from them because we would expect Valentine's Day scores to be higher in general, and that would mean that we end up with a positive t-score eventually, right? So you could do it either way, but you need to understand the interpretation of the t-score and compare it to the appropriate t-crit. So let's go ahead. I'm just going to type in equals this first participant's amount they spend on Valentine's Day, which is none, minus the amount they spent on Halloween. I'm going to hit enter. And then all I have to do is drag this all the way down, right? Just drag that all the way down. And those are all the difference scores for each of our participants. Now, I need to find the average, the mean of those difference scores. Okay, so I'm going to write mean down here equals average. And I'm going to figure out for all of these difference scores, remember, not the original raw data, the difference scores is what you're interested in for a dependent samples t-test. The mean difference the mean of the difference scores, okay, is 3.7. 3.7. Okay, so on average, what this means, on average, people are spending 3.7 more dollars on Valentine's Day compared to Halloween. All right. Now, we want to know, is this average, which represents, the average of the differences, is that going to be statistically significant? Statistically significant. Okay, so representing the difference between these two variables on average. Well, in order to convert that to a t-score, we need to divide it by the standard deviation of the different scores over the square root of n, and this is also the estimated standard error here. So why don't we go ahead and do that? We're going to go standard deviation of the different scores, standard deviation of the different scores, stdev dot s of all these guys. Okay, so there's the standard deviation. Let's go ahead, just for funsies, and calculate the estimated standard error. Remember, we'd still need to use the square root of n, and we could just look at it because we've already calculated it several times, but the square root of 20, 4.47. So now I'm going to put the estimated standard error, and that is equivalent to this bottom part right here, the standard deviation of the difference scores divided by the square root of n. So if I ask you to calculate estimated standard error, in this case, that's how you're going to do it, right? Okay, so that's estimated standard error, but we don't have the t-score yet, so let's find what that is. The t-score is going to be the mean of the difference scores divided by estimated standard error. Or you could just do it piecewise, and you could say the mean of the different scores divided by the standard deviation of the different scores over square root of n. You can do it however you'd like, but you do have to know how to calculate estimated standard error if I ask you that question, right? So this is going to be equal to our mean of the differences divided by, I could click on estimated standard error and that would be it. Or I could actually do, parentheses, standard deviation divided by square root of n. Either way is going to give me the same answer. That t value is 0.28. Now your spidey senses, your t-crit senses should be tingling right now. How does a value of a t-score of 0.28 feel to you? Is that high? Is it medium? Is it low? It's pretty low. Like that's actually quite low. A t of 0 would mean that essentially there is no differences on average at all between these two variables. That's what a t of 0 would mean. And so this is indicating, well, this looks like it's going to be a pretty small value, and we're going to compare it to the t crit. Okay. Well, to figure out what the t crit is, degrees of freedom for a paired sample t-test are n minus 1. We're going to have a one-tailed test with alpha is 0.05. So let's figure that out right here. Go back to the t-table. 20 minus 1 gives us a degrees of freedom of 19. One-tailed hypothesis with alpha is 0.05. 1.729. 1.729. 1.729. Okay, let's go back here. 1.729. And in this case, we would have been interested in the positive version because we thought that people were spending more money on Valentine's Day compared to less money, or I'm sorry, more money on Valentine's Day compared to expenses on Halloween. And we found a positive mean, positive t, comparing it to the upper end of the distribution, the t distribution. And what do we find? Yeah, unfortunately, our observed t is not even close to, and certainly not more extreme than our t-crit. Therefore, we fail to reject the null hypothesis. Again, the null hypothesis being that these two groups on average, or rather these two scores on average, are not statistically significantly different from each other. And that is what we found. Well, we retain the null. We can't prove that it's right or anything like that. Doesn't mean it's true. We just don't have any evidence to suggest otherwise. Okay. Almost there. We've got one more. This one's going to be for all the marbles, though. The independent samples t-test is definitely going to take a bit of doing. So let's go see what our question is here. I think people who play Pokemon Go spend a different amount of time outside on average compared to people who do not play Pokemon Go. All right. So, first of all, this is going to be a one-tailed test or a two-tailed test. It's going to be a two-tailed test, right? Because I'm not saying that people who play Pokemon Go spend more or spend less time outside, just that they'll spend a different amount of time outside. So that's a two-tailed test, non-directional. And when you look at a question like this, where it's comparing two different groups on some outcome, in this case, people who play Pokemon Go versus people who do not play Pokemon Go, and the outcome being how much time they spend outside, you're talking about an independent samples t-test, right? These are two different groups of people, and we're going to measure them on the same variable, in this case, amount of time outside, and compare those. So let's go back to our data. Okay, so we can see all the different people who do and do not play Pokemon Go and the amount of hours they spend outside. Well, unfortunately, the data are not set up in a very conducive way to calculate things like means and standard deviations and that kind of stuff, or sums of squares or anything like that. So we're gonna have to pull out the amount of hours people spend outside, whether they're Pokemon Go players or not. So let's make a couple new columns. I'm gonna say this will be like, or actually, I'll just say this is Go yes, and another column that is Go no. And what we're going to have to do is pull out all the people, all the amount of time that the hours people spend outside for all the people who do play. So this first person plays and they spend an average, or they spend 5 hours, okay, outside. No, 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 no. This person is a yes. They spend 7 hours. The next person is a yes. They spend 9 hours. The next person is that's a yes does six, then five, then eight, then four, then five. I think that's right. So we got 5, 7, 9, 6, 5, 8, 4, and 5. All right. How about the people who do not play? The first person has 6 hours, then 4 hours, then 2 hours, 6, 4, 2, then 3, then 4, then 7, then 3, then 3, then 2, then 2, then 1, then 2. Let me see if that's right. So we got 6, 4, 2, 3, 4, 7, 3, 3, 2, 2, 1, and 2. All right. So here we go. We're going to be doing an independent samples t-test to see if the people who do play Pokemon Go have, on average, a different amount of time spent outside compared to people who do not. So in order to do that, and remember, here's where we want to end up, all of this good stuff on the right side, I'm going to first have to calculate the means, because ultimately we need the means to be able to calculate the standard, the sums of squares. So let's do that. So this is mean and mean equals average. These groups of numbers here, over here equals average. These numbers over here. Okay, so we've got the means, and they look different, but we don't know if those are statistically significantly different yet. So we got the means. We don't have to worry about the population means, just the sample means. Now we're going to jump down to the pooled variance. Pooled variance, okay? And this is calculated by adding the sums of squares for the groups divided by the degrees of freedom. So we're going to probably want to calculate the sums of squares here. Sums of squares, in order to do this, you need a new column. Remember that the sums of squares originally comes from the standard deviation equation, where you would take different scores, so each raw score minus its category mean. That would create different scores. Then you'd square those different scores, add them all together. That would give you sums of squares. So we need the different scores are also called deviations. Deviation. I'm going to have to do it for both of these groups, right? So we can call them deviations or different scores. And it's not too bad. You'll remember from way back when we've done this before. You hit equals, you get the first person's raw score, and you subtract the mean from that, because that gives you the difference from the mean, or the distance from the mean. But you've got to do something, which is put dollar signs around the second letter. Okay, in this case, it's an I, which is kind of hard to see. You got to put those dollar signs in so that we're always going to subtract each of these numbers or the mean from each of these numbers, okay? And you can check, does that make sense? Well, 5 minus 6.125 should be negative 1.125. So that seems to make sense. Okay, so we've got our deviation scores for people who play Pokemon Go. Now we need the deviation scores for people who don't. First person's score minus the mean. But again, we've got to put in these dollar signs. Okay. 2.75, that seems right. 6 minus 3.25, that seems right. Drag this down. We've got all the deviation scores, but we're not there yet. We haven't calculated sums of squares, but there's a function for that. It's SUMSQ. SUMSQ. And that allows us to, what that's doing is taking all the deviation scores and squaring them and adding them together. You do have to have the deviation scores. If you try to do the sums of squares on the original raw scores, you're going to get the wrong answer. So make sure you do calculate the deviation scores. SUMSQ, all these deviation scores, boom. Now we've got basically this top part figured out. Again, this denominator here is, you could think about it as the number of people in group 1 minus 1 plus the number of people in group 2 minus 1. Or you could think about it as the total number of people minus 2. So it's up to you, however you feel comfortable with that. Well, there's 1, 2, 3, 4, 5, 6, 7, 8 people in this group, so degrees of freedom for that group would be 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 people in this group. So degrees of freedom for that group would be 11. So you could do it that way. Or since you know we have 20 people in the entire sample, right? Like we have 20 participants total, you could just subtract 2 from that. That might be the easier way to go. So we're going to calculate pooled variance, which you could label pooled var if you want, or write it out. I'll slide this over a little bit. So the pooled variance equals, I'm going to throw in some parentheses, sums of squares for group 1 plus sums of squares for group 2, right? That's what this is saying, divided by, I could again either do the degrees of freedom for this group plus the degrees of freedom for this group, or you could just see how many people are in the total sample minus 2. And that's what I'm going to do right now, which is just 20 minus 2, right? Should give you 18. Ooh, beautiful. Okay, so that's our pooled variance. And now, just like Russian nesting dolls, we gotta slot that one into this next equation in a couple different places. And that way we can get the estimated standard error. And then we can slot that into the ultimate t t equation for an independent samples t-test. So we've got this number. Now we've got to go for estimated standard error. And what I like to do, you could probably try to do it the square root of all this stuff all combined, and be fancy about it, and it would take a lot of parentheses probably. But I like to just calculate kind of this inside part of it before I take the square root of that. You can do it however you feel comfortable. And I don't know what to call this, but maybe I'll call it like inside estimated standard error or something like that. I know that's a little confusing, but basically what that is, it is equal to, and again, we're going to throw down some parentheses. Remember, it's the pooled variance, which we just calculated, over sample size for group 1 plus the pooled variance over sample size for group 2. Okay, well. We got pooled variance divided by how many people are in group 1? We just said 1, 2, 3, 4, 5, 6, 7, 8, right? Close those parentheses off. No, wait a minute. I didn't do that quite right. No, there, I did. Okay. I was looking at the wrong equation for a second. Okay. So yeah, we've got that, and then we're going to add to that the pooled variance again, divided by the number of people in this second group, which again was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Beautiful. All right. So that's just sort of like this inside portion taken care of, but that's not the estimated standard error. Estimated standard error is going to be the square root of that. So you can do equals SQRT as the function for the number we just calculated. And that is the actual estimated standard error. And you're almost certainly going to have to do that on the exam. So you definitely want to know how to do that. So now we've got pooled variance, we've got estimated standard error. We've got pooled variance, we've got estimated standard error. We can plug in the estimated standard error into the denominator of this equation, and we're there, right? So we're going to calculate the t-score now. The t-score is equal to the mean of the first group minus the mean of the second group. In this case, since we're using a two-tailed test, you can do it in either direction. It doesn't matter at all. You could take this minus this or this minus this. Let's just go this minus this. Um, Actually, I'm going to put in some parentheses. Whoop, 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 whoop. Uh-oh. Throwing a fit over here. Okay. Throwing in some parentheses, dividing that by now our estimated standard error that we just figured out. Okay. 3.6. 3.6. Nice. Now, again, we're going to have to compare that. Our original hypothesis is we just think that people who do play Pokemon Go will have a different average amount of time spent outside compared to people who don't. So are these numbers statistically significantly different? That's what we're trying to find out. The null hypothesis, again, is that they are not different. At least they are not different in the population, right? Okay, so let's go figure out with a two-tailed test, alpha is 0.05, degrees of freedom of n minus 2, if we've got our t-crit. So 20 minus 2, 20 total people, minus 2, the degrees of freedom are 18. A two-tailed test at alphas equals 0.05. 2.101. 2.101. Is our observed t more extreme than the critical value of t? Yes, it is. Therefore, we know we would end up in the critical region, and that means you get to reject the null hypothesis. What's the null hypothesis? That these two sample means are the same. Well, we reject that and conclude that, in fact, uh, people in the Pokemon Go group do have a different amount of time spent outside on average compared to people who don't play Pokemon Go, and in a specific direction, which is such that they actually spend more time outside, right? Even though that wasn't part of we didn't have a directional hypothesis, it's still the case that these two numbers are significantly different, and in which direction Pokemon Go players spend more time outside on average than people who don't play. All right. I hope that was interesting. Best of luck on the exam, and I'll see you in the next video.